Members of the Diplomatic Corps, Professor Winston Moore, Deputy Principal, the UWI Cave Hill Campus, Mr. Elson Gaston, Deputy Governor of the Central Bank of Barbados, Professor Avril Williams, Professor of Supramolecular Chemistry and Nanotechnology, Faculty of Science and Technology, the UWI Cave Hill Campus, and feature speaker, Dr. Sherma Roberts, Interim Director, School for Graduate Studies and Research, the UWI Cave Hill Campus, Professor Emeritus Ishinkumba Kawa, the UWI Mona Campus, Dr. Luke Delmas, Senior Teaching Fellow, Department of Chemistry, Imperial College London, members of the university community, specially invited guests and family, members of the media, online audience, ladies and gentlemen, good evening. My name is Janice Badnock, Dean of the Faculty of Science and Technology and the chair of this professorial lecture, which is being delivered by my esteemed colleague and friend, Avril Williams. It is customary within academia to celebrate the elevation of a colleague to the rank of professor, the highest academic title, by way of a public lecture. Professor Williams, the first female academic in chemistry at the Cave Hill campus to achieve this rank, will mark this significant milestone in her career with her lecture entitled Beyond the Molecule, Unveiling the Nexus of Supramolecular Chemistry and Nanotechnological Applications. For those of you joining us, both in person and online, and particularly the chemists and students among us, I'm sure there is much anticipation of chemical reactions and unique chemical motifs. However, given the significance and setting of this occasion, I have been assured that this lecture will offer a compelling story that will draw us all into the marvels of this scientific field. I therefore now invite Professor Ishinkumba Kawa, Emeritus Professor, the University of the West Indies Mona Campus, to deliver opening remarks.
Distinguished ladies and gentlemen, my name is Ishinkumba Kawa. I'm a retired professor of supramolecular chemistry. I was interested throughout my career in the synthesis, structure, and physical and chemical properties of supramolecular assemblies. I met Avril in the late 90s when she was doing her PhD. She was working with Dr. Lincoln Hall, at that time. And they were making good molecules called squarates. They had very beautiful structures. They had very good physical characteristics, and lots of people wanted to have a hand on them. Those molecules were not easy to make. They were quite difficult. I do recall a conversation between myself and Lincoln when we were at Imperial College trying to figure out how to use facilities there to determine how our molecules look like. And Lincoln kept complaining about a nitrogen atom that they were putting on those molecules, and the nitrogen atom was falling off. And he says there was an atom, we put it in, a nitrogen atom, but when they looked with other measurements, the nitrogen atom was nowhere to be found. It turns out that actually they had put in the nitrogen atom, but the chemistry of the system was such that the nitrogen atom was falling off. And Lincoln Hall kept saying to me, I am going to talk to Avril. I am going to talk to Avril. When I speak to Avril, I'm sure we'll sort it out. And sure enough, it was not easy to speak at that time in the 90s. Cell phones were not available. WhatsApp was not available, and so on. So he had to wait until he actually went back to Trinidad to try and explore and quiz Avril and her team what it is that was actually happening. It turns out that we were able to resolve the problem because the nitrogen was actually put in, but somehow it dropped off. And once they sorted that problem, they produced wonderful molecules with wonderful structures and physical properties, molecules that other people wanted to have a hand on. And they have actually molecules with very good electrochemical properties, which can be used for online sensing of pollutants in the environment, disease markers in our bodies and animals, and so on. At that point, I realized that Avril was a very brilliant person, very calm, deeply focused, and very much enthusiastic about what she was doing, and certainly a very calm person who was needed to actually sort out that square problem to produce those beautiful molecules that I'm sure she will give you a hint of what they are in her talk. Now, she decided to go overseas and work with a Nobel laureate in California. She tackled what is up to today a very difficult problem. And that is the problem of making molecular interlocked molecules. And these are very difficult to design because the design parameters are not actually available, and they're also very difficult to make because the synthetic methodologies would have to be invented or would have to be found. But she was able to put her mind together and her efforts together, her brilliance together, and the experience, more importantly, the experience that she gained while working at the UWI at St. Augustine to make the first ever molecule, which they called soutens or soutens, depending on what you like. These are beautiful molecules with different endings and different components attached to them, as she will show you later on, and each one of those arms, each one of those components can perform different functions, can do a different dance, and every dance and every property actually leads to applications that can benefit humanity. She went on also to engage her brilliance and her skills in synthesizing dendrimers and a host of other nanomaterials. What is quite clear is that this brilliant daughter of the Caribbean has enormous potential. She still has quite a lot of time, ahead, and we do trust that she will continue to bless us with wonderful molecules as she has been doing. I want to thank her very much for doing us proud. I do recall when we were in London with Dr. Lincoln Hall, and we were looking at some of those professors and other research people at Imperial College, and they were talking about, oh wow, good things are going on in the West Indies. Good things are going on at the University of the West Indies. And it's thanks to Avril and people like her who make us proud as a people in the Caribbean, and certainly at the University of the West Indies. We want to congratulate her on her achievement. We want to congratulate her on a well-deserved professorship of supramolecular chemistry and nanotechnology. And we do trust that the Lord will bless her richly to continue sharing with us her knowledge, her skill, her imagination, and keep those beautiful molecules coming. Thank you.
Thank you very much for your remarks, Professor Kawa. I now call on Professor Winston Moore, Deputy Principal of the University of the West Indies Cave Hill campus, to formally welcome you to the Cave Hill campus.
Dr. Janice Badenoch, Dean Faculty of Science and Technology, the UWI Cave Hill campus, as well as tonight's Master of Ceremonies, members of the Diplomatic Corps, Mr. Elson Gaskin, Deputy Governor of the Central Bank of Barbados, Professor Avril Williams, Professor of Supramolecular Chemistry and Nanotechnology, I actually got it right, Faculty of Science and Technology, the UWI Cave Hill campus. Our featured speaker, Dr. Sherma Roberts, Director, School for Graduate Studies and Research, the UWI Cave Hill campus, Professor Emeritus Ishinkamba Kawa, the UWI Mona campus, Dr. Luke Dalmas, Senior Teaching Fellow, Department of Chemistry, Imperial College, London, members of the university community, specially invited guests, members of the media, our online audience, ladies and gentlemen, good night. Good night. Thank you so much. I bring you greetings on behalf of Principal and Pro Vice Chancellor of the Cave Hill campus, Professor Clive Landis, and the rest of the management and staff here at the UWI Cave Hill campus. Thank you very much for taking the time to be part of this event, and I therefore want to welcome you to the UWI Cave Hill campus, as well as the Walcott Warner Theater in the Faculty of Culture, Creative, and Performing Arts. Ceremonies are a key part of what we do at the university. I would say at the University of West Indies, but I would say at universities in general. Is perhaps this ceremony that we're having tonight is perhaps one of my favorite ceremonies, the inaugural professorial lecture of our newest professor. Given the important role that universities play in society, it should be acknowledged that university professors are the ones who give relevance to these institutions. Within universities, professors are supposed to be mentors to the next generation of academics. This includes students as well as young academics at the beginning of their careers. I should note, however, that a university professor does not only seek to create creatures like him or herself, they also tackle issues of tremendous importance to society. By applying their research skills to a particular societal problem, a university professor develops innovative solutions to intractable problems and therefore enhances societal well-being. University professors are innovators who also train the next generation of innovators. Therefore, their value to society cannot be priced in dollars and cents. I'm also personally keen to listen to tonight's lecture, given my own challenges with the discipline of chemistry. I would provide a lot more details, but suffice it to say, there was a conversation between my chemistry teacher and my mother, and they came back to me and said that under no circumstances will I be allowed to do chemistry at CSET. So I'm hoping to learn something tonight. I also take these lectures to really for us to really reflect on what it really means to be a professor, and a professor at the University of the West Indies. As tonight's chair mentioned, it is essentially the highest rank that an academic can achieve within the higher education environment. Hence, there's a very thorough and rigorous evaluation process that must be successfully undertaken and therefore completed before an academic can be awarded this title. So colleagues, let me give you an idea of what Professor Williams had to go through before she got that title of professor. First, a lecturer must build a body of research that makes a substantive contribution to the area of research, contribute to the university and departmental activities, support campus outreach activities, all while carrying a full teaching load. And if you're successful at doing that, you're promoted to senior lecturer. That's the first stage. Then after you're promoted to senior lecturer, you then have the ability to apply for the post of professor at the university, the rank of professor at the University of the West Indies. And to be promoted to the rank of professor, your contribution to your field of study is first assessed by academics within the UWI. And if your colleagues think that you have the right stuff, your CV, papers, and other supporting documents are then sent to external academics from some of the finest universities around the world. And they're asked one very fundamental question: would this individual be a professor at your university? And Professor Williams' evaluators or external assessors were from some of the finest universities that you would ever come across. And they all came back and said the same thing. This individual would be a professor at my university. I must also note that in the case of Professor Williams, she reached this benchmark while also serving as a lecturer, head of department, dealing with resource limitations in the Faculty of Science and Technology, and in between all of that, finding time for family and friends. So this accomplishment is truly outstanding. Ladies and gentlemen, I will not take away any more time from the start of this evening's show, but just to say thank you very much, Professor Williams, for allowing us to hear and listen to you tonight.
Thank you very much, Deputy Principal, for your warm welcome. I am convinced if you were in our classes, you would be getting the chemistry quite fine. Ladies and gentlemen, I am pleased to invite Dr. Luke Delmas, BSc, MPhil, UWI, MRes, PhD, Imperial College London, current Senior Teaching Fellow, Department of Chemistry, Imperial College London, and more significantly, former research student of Professor Williams, to introduce our featured speaker, and after which Professor Williams will take the stage.
Good evening and welcome again everyone attending tonight's proceedings, both in person and online. I'm sorry that I can't be there in person myself to raise a glass on this momentous occasion of Professor Williams' inaugural lecture. It's a great honor and privilege, as one of her previous research students, to have the opportunity to introduce her and the groundbreaking work we'll hear more about shortly. Professor Williams is a Trinidad and Tobago national whose academic journey began at UWI St. Augustine, where she completed her undergraduate studies. This experience ignited her passion for chemistry research, and she stayed on to pursue a doctoral degree under the mentorship of Professor Lincoln Hall, graduating in 2001. During her PhD, Professor Williams studied the coordination chemistry of squaric acid-derived ligands. Her research provided an in-depth understanding of the structure and electrochemical properties of these compounds. This work then led on to investigations of the mediating properties of squaric ligands in the glucose metabolic pathway using electrochemical techniques for biosensor applications. This whole period of work exemplified the hallmarks of her unfolding career: interdisciplinarity, collaboration, and global reach. Driven by application-led research, this work laid the foundations for advancements in smart electrode materials and novel sensing techniques, particularly beneficial for resource-limited regions. This exciting chemistry also nurtured an ongoing international collaboration with Professor Emmanuel Iwoha at the University of the Western Cape in South Africa. A budding global citizen, Professor Williams then undertook postdoctoral studies at UCLA's California Nanosystems Institute under the mentorship of the late 2016 Nobel laureate Sir Fraser Stoddart. During this time, she made significant contributions to the field of mechanically interlocked molecules, including realizing the first example of a novel class of supramolecules called soutanes. Sir Stoddart himself dubbed her the tailoress of these new molecular architectures, recognizing their potential as prototypes for artificial cell-like assemblies. Following a short postdoctoral placement at the University of Maryland, College Park, Professor Williams joined the UWI Cave Hill community as a lecturer in inorganic chemistry in 2004. She was granted indefinite tenure in 2012 and promoted to senior lecturer in 2013. Her dedication and leadership led to her historic appointment as the first female head of Department of Biological and Chemical Sciences at UWI Cave Hill in 2018. Professor Williams' commitment to excellence applies also to her teaching, where she has been recognized for her outstanding contributions to student learning and to curriculum innovation. In 2023, she played a pivotal role in establishing the Center for Commercial Analytical Services, Cave Hill's first for-profit center. She also serves as a board member of the Sagicor Cave Hill School of Business and has consulted with various Barbadian governmental ministries, private sector companies, and the UN Environment Programme's regional office. What I've shared so far highlights the broad range of Professor Williams' research activity and academic service, and she's not finished yet. However, I'd also like to take a moment to reflect on Professor Williams as a role model. As my own career develops, I often reflect on my formative years at UWI Cave Hill while working in the Williams Group. Professor Williams took a personal interest in all of her students, sharing her insights and supporting us on our journey to becoming scientists. She was there whenever we needed her. We discussed the literature, troubleshooted reactions, assigned complicated spectra, and so on, usually along a line of Socratic questioning that taught us how to think. She encouraged us to bring our unique perspectives and creativity to the laboratory and provided us room for growth and exploration while being available to give us advice and guidance. We held joint research group meetings with the organic synthesis group of Dr. Janice Badnock, and all benefited from this collaborative exchange of knowledge and experience. This showed us that chemistry was most enjoyable when shared among a network of colleagues. Indeed, Professor Williams emphasized the importance of being active members of the broader scientific community. I vividly remember attending my first international conference in 2010, hosted by UWI Mona at a local resort. Professor Williams had secured funding and encouraged us all to come along, opening our eyes to the breadth of cutting-edge research from around the world and making us feel a part of this global chemistry community. Professor Williams' unwavering attention to detail is evident in every task she undertakes. I can recall as research students the rounds of proofreading and editing of our work which she assisted us with so willingly. I remember the numerous practice sessions for oral presentations and pro tips for slide design and creating impact. She wanted to ensure that we went out into the world with meticulous writing skills and that we developed our own voices with the confidence to communicate our ideas clearly and effectively. We all recognize the importance of pastoral care and well-being within our higher education communities. Reflecting on my time at Cave Hill, I deeply appreciate how Professor Williams went above and beyond in her care for all of us. I see it now as our duty to pay that kindness and generosity forward as we strive to create a brighter and more supportive world through collegiality in everything we do. Now back to tonight's proceedings. As the first female professor of chemistry in the Faculty of Science and Technology at UWI Cave Hill, Professor Williams continues to break boundaries, and seeing her career progress has been incredibly motivating for so many of us. As a Trinidadian professor of supramolecular chemistry and nanotechnology, her visibility is crucial in breaking stereotypes and promoting inclusivity in science. Her achievements demonstrate that scientific excellence transcends race, gender, and nationality, inspiring others to pursue their passions regardless of background. Her success encourages us all to strive for excellence and underscores the importance of diversity and inclusion, ensuring everyone has a seat at the table as we work together as a community to solve the world's problems. Distinguished guests and colleagues, please join me in congratulating Professor Williams on her remarkable achievements and in inviting her to deliver her professorial lecture entitled Beyond the Molecule, Unveiling the Nexus of Supramolecular Chemistry and Nanotechnological Applications. Thank you.
Good afternoon, everyone. If I were one to cry, I would be crying all now. But everyone who knows me knows that I don't shed a tear and that I am all about tough love. So I just want to clear up something there. You know when Professor Kawa said that we had to figure out where the nitrogen was going? If I tell you how we figured out where the nitrogen was going, I burnt up the sample. Not intentionally, but the sample burnt up. And at the bottom of the ashes of the sample was this perfect crystal. In fact, the X-ray crystallographer at Imperial College said that this was the most perfect crystal he had ever seen. And that was actually a crystal of the intermediate. And therefore, we were able to figure out the mechanism and see where the nitrogen was actually going. That is to say to my students that not everything that you're looking for is what you should find. Things happen for a reason. Yeah. Okay, so today, I struggled a bit with this talk, mainly because I didn't know where to pitch it. So you all see the title, right? Enough people tell me about they're not going to understand anything and therefore they're not coming and all of that jazz. Yes, the acting director, I think I heard her in academic board say, well, y'all wouldn't understand what she says anyway, when she was advertising the talk. So I decided that this is a lecture, and therefore my goal at the end of this lecture is to make sure that everyone, once I'm finished and you leave here, you know what is supramolecular chemistry, you know what is nanotechnology, you know how both of them can work together to create wonderful things. So that when somebody asks you, as I say to my students, and when somebody comes up to you in a cocktail party and says, "What is this?" you'll be able to answer. I am happy that I'm giving this talk because, not because I'm a professor or anything like that, that's just icing on the cake. But it has been my experience that when I go to cocktail parties and people ask me what I do, I say I lecture at the University of the West Indies, and they're like, "Oh, that's nice. What do you lecture in?" "Chemistry." "Oh, well, I didn't like chemistry at secondary school." Or apparently some people were barred from doing chemistry at secondary school. And then they say, "So what area of chemistry?" "Inorganic chemistry." "Organic chemistry?" "No, inorganic chemistry." "Oh, okay, that's nice. So what is your research in?" "Supramolecular chemistry and nanotechnology." And usually that is the end of the conversation. Yep, there's an awkward silence, and then we have to find something else to talk about. So I see it as my role to get the information out there so that not only the young people, but those of us who are parents, etc., can then speak to our students about this type of science. Oh. So we all know, most of us inside here have done some sort of science, some sort of chemistry. So we know that we take molecules, yep, and we can form these strong bonds between these molecules. That's what the chemical is. So we take A, we react it with B, and we get C. And that is a strong bond. But with supramolecular chemistry, we can take A, and we can take B, and we can take the interactions that exist between A and B and make all different versions of AB. It's just left to your imagination. And what holds the A and the B together are weak intermolecular forces. And that is the crux of supramolecular chemistry. Weak intermolecular forces, not the covalent bond that the students know about or you may know about, not strong bonds, but very weak bonds. Now you might say that things like nanotechnology, you've heard about it, and these things don't exist. These things exist in books, in labs, etc. So I want to draw your attention to, anybody know who this is? Nobody's played tennis? Roger Federer, young Roger Federer. And he is holding a Wilson racket that is made of silicon nanoparticles. And this was a long time ago, something like 2009 or something like that. And then we have this cyclist who's riding a bicycle that has carbon nanotubes as part of it. And interestingly, of all the carbon nanotubes that are manufactured in the world today, 14% is used in sport, in the sports arena for the gear, because we want things that are light and strong. How many of us wear sunscreen? No? Most people should be putting up their hands. So we, as people of color, know that when we put sunscreen on our face, we look like ghosts, because you can see the cast, right? And then they've made tinted sunscreen, but still you gotta find your color and match it, etc., etc. But we now have sunscreen that has nanoparticles in it, as you can see here, nano zinc oxide particles, and therefore it absorbs into your skin seamlessly and gives you the sunscreen without any sort of stress. And you might think that these, again, are things in labs, but no. We actually have these for sale. So you can look for sunscreen that is made up of nanoparticles that will be absorbed into your skin and sometimes give you a little glow, or as the young people say, a glow up, something like that, yes. So as we go through, you're going to see other examples of both supramolecular chemistry and nanotechnology that is utilized today. But the crux of supramolecular chemistry, and I want you to keep this in the back of your mind, is that it has to do with weak intermolecular forces. So it's all about bringing molecules together using these weak intermolecular forces. And the word supramolecular actually means beyond the molecule. So supra, above, beyond the molecule, because we are designing as chemists molecules that then recognize each other to form more complex molecules. And anyone who has ever been in a lab knows that when you introduce complexity, you introduce stress, you introduce cost, you introduce time. So we have found a way where we can design simple molecules that would recognize each other. Once we've designed the simple molecules with the strong bonds, we just throw them together, and they find each other and bind using weak intermolecular forces. So throughout my talk, you're going to see some common themes going on. So we're going to talk about medicine, environment, materials, as well as energy, and there's a little bit of computing in there as well. So as we said, supramolecular chemistry, weak intermolecular forces, we are focusing on the forces that bring the molecules together. And why would scientists even want to do this? Because of the fact that if we can control and manipulate these small molecules, then it opens up a whole area like drug delivery systems, like sensors, like smart materials, as you will see as I go through my talk. Things that are useful and apply to the challenges that we have today. So before we get into the actual weak forces, I want to bring to you some concepts with respect to supramolecular chemistry. So a core concept of supramolecular chemistry is host-guest chemistry. What that means is that you have two molecules, minimum two molecules. One is a host and one is a guest. Usually the host molecule is larger than the guest molecule. So the host molecule exists, we make that in the lab. The guest molecule exists. We can make this in the lab, or it can be out there in the environment or in your bodies, etc. And the guest molecule would sit within the host molecule. So it's almost like a lock and key, right? If we have a lock and key, which one would be the host? The lock. So the lock is the host, and the key fits in. And just like how the key is made for the lock, the same way we as chemists would design the host to complement the guest, such that we can capture the guest as seen here. And one example of a host molecule is cyclodextrin. As we will see, cyclodextrin is very important and it is utilized in a lot of products today, and as well as crown eaters, which can encapsulate metal ions. So crown eaters have been used in, and I see that Dr. Kohol just came in, Faculty of Medical Sciences, valinomycin. Everybody knows valinomycin, an antibiotic. Yes, it contains a crown ether as the host molecule. So you have been ingesting these things already. So it's not something that's out there, it's not something that's in a lab, it's everywhere. So I'm just going to play a short video for you so that you will have a feel for what cyclodextrin does and what host-guest chemistry is all about.
What do many fragrances, deodorizers, flavorings, and even drugs have in common? The answer lies in the tiny hole inside cyclodextrin, a ring-shaped molecule made of naturally occurring sugars. When it's used in deodorizers, the hole inside cyclodextrin can trap unwanted odor molecules. When it's used in drugs, the hole can carry medicines that can then be delivered to the affected part of the body. Cyclodextrin has a natural ability to trap other molecules because on the inside it's hydrophobic, or water repellent, and on the outside it's hydrophilic, meaning it's attracted to water. With its characteristic donut shape, cyclodextrin acts as a host that encapsulates guest molecules inside the donut hole. When host and guest molecules bind together loosely, through weak intermolecular forces, they form a supramolecule. The challenge is to create useful molecular host with spaces large enough inside to surround the target guest molecule.
So that essentially shows you how host-guest chemistry works. And I hope from the video you realize that the guest fits nice and tight within the host. So the host is actually designed for the guest. So who knows this product? Nobody here? One person, two people. Patches, Nicorette, to help you quit smoking. That contains cyclodextrin. I think everybody has this at home. Yes? Voltaren. Indeed, has cyclodextrin in it as well. All the allergies sufferers, Zyrtec, has cyclodextrin in it. So these are things that are on our shelves right now that exploit host-guest chemistry. Of course, we have all the others that we can go into, like Febreze, where we spray, to pick up the odorous particles, etc. But then we would be here whole day just talking about host-guest chemistry, and there's a lot more to see. So another concept in supramolecular chemistry is self-assembly. So whereas with the host-guest, you saw that the host was a different size to the guest. In self-assembly, all the molecules are of approximately the same size. And then they're assembled using these weak intermolecular forces. So things like cell membranes come together because of the weak intermolecular forces, and cell membranes are actually what we would consider to be a supramolecular complex. It was just made by nature, not us yet in the lab. Then we have molecular recognition. And this is what I talk about when I say that we design the molecules to recognize each other. So you put in the actual design into the molecules and they recognize each other at that particular scale. And a common example of that is, of course, the DNA base pairs. So adenine binds to thymine and guanine binds to cytosine using hydrogen bonds, which is one of those weak intermolecular forces. So we have the molecular recognition coming together to assemble the double helix of DNA. So we would also consider DNA to be a natural supramolecular complex. Made by nature, but that's where scientists learn from. Other key concepts in supramolecular chemistry are things like dynamic chemistry, and this is where we start to get fancy, because now we can make molecules that can open and close. Because remember, it's only weak forces that's holding them together. So if we can manipulate the forces, then we can get them to open when we want it to open and close when we want it to close, which means that now we have drug delivery systems that we can design and make. Then you have supramolecular polymers, where you have polymeric strands that once again self-assemble through weak intermolecular forces. And these have their own applications, as we shall see shortly. But what are these weak intermolecular forces? You already heard about hydrogen bonding. Everybody knows hydrogen bonding from water. So hydrogen bonding, you have the water molecules actually bond together via hydrogen bonding. Water, ice, the same thing. But did you all know that hydrogen bonding is responsible for Kevlar. What's Kevlar? The bulletproof material. It's a hydrogen bonded polymer network. And because of the millions of hydrogen bonds that you have there, that gives the material the resistance that is needed to stop a bullet. Then we have van der Waals forces. So, sorry, that's hydrogen bonding. We have van der Waals forces, and I'm not sure how you explain van der Waals forces to people. But if you close your eyes for 1 second and don't fall asleep, just close your eyes, and imagine that you are slow dancing with someone. You are not holding on to that person tightly at all, right? However, you are influencing your partner's movements. Your partner is influencing your movement, even though you are just, resting your hand there. And you may sway backward, and you may sway forward. It's the same thing that happens with van der Waals forces. So within molecules, you would have the electron density move to one side of the molecule, and then to the other side of the molecule, and therefore molecules will become attracted because of that movement. If you want to know more, there are textbooks for that. Pi-pi interactions. So imagine a stack, you have 2 stacks of cards, right? If they are in their own pile, they stack one on top of the other. And this is exactly what pi-pi stacking is, except we use rings in chemistry that stack one on top of the other. And the interaction between the rings is what's called pi-pi stacking. Now, if you bring the 2 stacks together and try and throw them into each other, you will find that there are some that are offset from the other one. And that's another type of pi-pi stacking. So you can have directly over, or you can have offset. Both of those is a type of interaction that occurs between molecules. Electrostatic forces is easy. Everybody has table salt at home. No? Yes? And table salt is sodium chloride. So sodium ions and chloride ions, and they are attracted to each other because one is positive, one is negative, and that is electrostatic interactions. You also, maybe when you were smaller, you rubbed a balloon on your hair, and your hair stood up, an electrostatic interaction. And then we have metal coordination. Now, metal coordination is where you have a metal and it is bonded to different molecules. So you can imagine it to be a parent at a play park with 6 children. That parent be in the metal center. You can have 2 children holding on to the parent's arm, 2 children here, one holding on to the belt, one in the back. It's the same way that the ligands attach to the metal center. And just like how one of the 2 children holding on to the right arm can come to the front, same thing happens with these molecules. So they change geometry around the metal center, and that in itself allows us an interaction that we can then manipulate. So there are other interactions, weak interactions that occur in supramolecular complexes, but these are the 5 that are most useful to supramolecular chemists. So now that we know about the different interactions, what are some of the applications of supramolecular chemistry? So you heard me speak about drug delivery systems. We can create molecules that respond to the environment. We can get them to close up, and we can get them to move and go somewhere else and then open up at the other side, just by applying external stimuli. Of course, we can utilize, as you saw with the cyclodextrin will protect the drug as well. So it will keep it from, I was going to say becoming oxidized, from degrading. Yes, it will keep it from degrading. It would also make it soluble because there are lots of drugs that are not soluble in aqueous system in the body, and therefore these host molecules can make them soluble. No, I want to go back. Hold on. Material science, we can make smart materials, as you will see later on in my talk, that can adapt to the environment in which we are. Things like self-healing polymers or responsive gels. Nanotechnology is where we wait for the end for that, but supramolecular chemistry plays a big part in nanotechnology. Other applications, we have molecular machines where we can look at things like information storage, for instance, because molecular machines are all about movement. And molecular machines were awarded the Nobel Prize in Chemistry in 2016. So not only can we make these molecules, but we can get them to move at the nanoscale level. Then we have sensors that can be used for detecting ions and with high selectivity. So you can use sensors to detect biomarkers, for instance. You can give a farmer a sensor, take it out in the field, and the farmer can get real-time information from the sensor. We have catalysis. We have materials that can mimic enzymes. So we can increase the reaction rate as well as the selectivity of different reactions. And of course, we have environmental applications where we can take materials, and when I say materials, I mean supramolecular materials, these supermolecules, and we can actually clean up the environment. Because as you will see, not too far, their recognition allows for this sort of application. What are some of the advances? We have mechanically interlocked molecules, and this was my area of research as a postdoctoral scholar. So a mechanically interlocked molecule are two or more molecules that are connected to each other, but not by the traditional bonds. So think about your key ring. You have your key ring, and then you have keys on the key ring. The keys on the key ring are not attached to the key ring. They're not part of the key ring. But in order to get a key off, you have to open up the key ring. So the same thing happens with these mechanically interlocked molecules where they are connected to each other, but we can also take them apart by breaking a bond. And it's the mechanically interlocked molecules that allowed for the first set of movement within these supramolecular complexes and gave us molecular machines. We have artificial photosynthesis. So imagine that we can take a supramolecular complex that can imitate the enzyme that splits water. And therefore, as a result, we can produce things like hydrogen and electricity from solar energy. Soft robotics, we need complexes that can interact with delicate objects, that can interact with humans, and therefore, this is where hydrogels and elastomers come into play. And then we have electronics, of course. So, because when we get down to the nanoscale, you will see how some of these supramolecular systems can actually be used as, for instance, nanowires, because of their conductivity. So some example of supramolecular structures, you have seen cyclodextrins already. Over here, crown eaters are these these ring molecules, as you see here, that tend to favor metal ions in the middle. Why am I keep hitting the wrong thing? And then you have metal organic frameworks, which are MOFs. And MOFs are where you have the metals coming together with the organic molecules to form these sort of structures. And the good thing about these structures is all the surface area that you have on the inside. So all the cavities that exist on the inside, which means that scientists are now looking at them as being applicable in the storage of gas. So we are always looking for moving away from gasoline and other fossil fuels, and we speak about the hydrogen fuel as running your car. But how are we going to store the actual hydrogen fuel? So we need things like MOFs that have cavities on the inside to store the hydrogen fuel. Then we have calixarenes, and calixarenes are similar to cyclodextrins except that, and crown eaters, except that they are more rigid. And because they're more rigid, they tend to be more selective as to what they bind to. And therefore, calixarenes tend to be used a lot in sensors. So imagine you want to go out there and you want to look at how much in your wastewater any particular analyte, it could be a hormone, for instance, that you want to look at in wastewater. You can design a calixarene that would bind to that particular analyte and give a signal upon binding, and therefore be able to detect the hormone. And then we have dendrimers, and dendrimers, you see a picture of it a little later on. A dendrimer is a spherical supramolecule. It's tree-like. And dendrimers are good for imaging because we can put, so anybody here ever did an MRI? Yes? So they give you a contrast agent, right? Because they want to see certain things in your body, certain organs, etc. Dendrimers can hold that particular contrast agent within its structure. We can then, on the outside of the dendrimer, add receptors that would make it go straight to the heart if that is what you are trying to look at. So the dendrimer will take the contrast agent straight to the heart, and then we can manipulate the dendrimer to release the contrast agent. What does that do? It makes now, we are heading towards precision dosing. So you don't have to give the individual more than is needed, because you know if you just take it into your system, it goes all over the place. So you usually have to give more than is required. So you have the contrast agent going directly to where it is, and therefore the toxicity of the contrast agent is also reduced. Even though we have lots of uses for supramolecular chemistry, there are challenges associated with supramolecular chemistry. First, complexity in design. So essentially, we are working with very, very, very small molecules. And when you introduce complexity, you may introduce unexpected, unwanted interactions. So you want the molecule to interact a certain way, but the molecule may decide that it's going to interact with other things, and we need to get control of that. Stability of the non-covalent interactions, we need to be, our supramolecular complexes, because they are made and held together with weak forces, we need these weak forces to be stable, because these complexes are going to be in different environments, like different temperatures, different pHs, different light, for instance, and we need it to be reliable, stable and reliable. How are we going to scale this up? So we build these things in the lab, but then we need to get it to industry, and industry needs to mass produce it. So we need to look into how you do that in a cost-effective manner, but also a reproducible manner, because every time they make it, it must be the same thing that is being made. And then integrating with existing technologies. So we don't want to do a quantum leap. We want to utilize the progress that we have made to help out industry and their varying technological challenges that they have. And therefore, we have to learn to integrate these complexes that we have made into what already exists, so that we have a bit of continuity as we progress and go along. So some key takeaways for supramolecular chemistry is that it is all about the manipulation of the weak forces. It is the weak forces, hydrogen bonds, pi-pi interaction, van der Waals forces, I can't remember the electrostatic forces and metal coordination that are responsible for us being able to make these very complex systems that we can control. Now, nanotechnology. No, first, soutines. So this is the molecule that both Dr. Delmas and Professor Kawa spoke about. This here is called a mechanically interlocked molecule. Remember the key? Right. So this is a dumbbell and this is a ring. And the ring cannot come off of the dumbbell unless we break a bond. So this is a rotaxane, and this has existed for quite a while. And this is one of the molecular machines that was awarded the Nobel Prize in 2016. And my project essentially was to take that 2-rotaxane and convert it into cetane as a prototype. So essentially, why do we even want to do that? It was to show that we can build in complexity in a reproducible manner at that particular level. And therefore, it took me a while, but we eventually got to the cetane. And for the chemists that are in the house, yes, you see some actual chemical structures. As you can see here, we made all 3 of these 2 we bought commercially. So we made these 3 molecules in the lab, and then we threw all 5 of them together in a solvent. And they came together and formed that, all on their own. Now, there really is no way to go into the lab and try to make this using a statistical method, because you will be there forever. So all of this come together on its own, remember, molecular recognition, on its own to form this, and you can see how tightly all the pieces come together because they recognize each other and they are comfortable with each other. So that is where they stay. And we can get this molecule in about 100% yield easily because we're not doing anything. The molecule is deciding that it's going to come together. So that was the kind of work that I do in supramolecular chemistry, which is the design of the molecules. This here was done by Dr. Luke Delmer. So again, looking at the different structures that you can make, all using molecular recognition and those weak intermolecular forces. And this is my current grad student, and this is what he is attempting to make, which is, he calls a handcuff catenane. Handcuffs, and the ring a catenane. His own name. Okay, so nanotechnology now. We move on. Everybody has heard about nanotechnology. I know people have never heard about supramolecular chemistry, but they've definitely heard about nanotechnology because it has been around for a while. So nanotechnology is all about dealing with molecules that exist between 1 to 100 nanometers. And why do we want to go down to that particular level? Because we get unique physical, chemical, and biological properties at that level. So you can take a particular compound in its macroscopic state, and it has a certain property. And then you break it up so that it gets to the nanoscale level, and you have a totally different property. So what you see at the nanoscale level are things like enhanced strength, better conductivity, unique optical properties, as we shall see. And we can utilize all of those in medicine, in electronics, smart materials, energy, and to, of course, pollutant control. So energy, things like transistors. Now, way back in 1959, Richard Feynman, who is known as the godfather of nanotechnology, said, while giving a lecture at Caltech, the principles of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. It is not an attempt to violate any laws. It is something that can be done, but in practice, it has not been done because we are too big. So way back in 1959, he was essentially telling us that we need to get to the nanoscale level. And I am sure that he is very happy now because you have a whole host of chemists who are working on the nanoscale level. But, as I say to my students, right? If you were to encounter the reasonable man in Black Rock, and he asks you, what is a nanometer, what are you going to say? So we all did math, so we know about a nanometer. They're going to say a nanometer is a billionth of a meter. Okay, I don't know how that helps the man in Black Rock. So this is a meter, right? About 3 feet. What's a billionth of that? Can you imagine it? No? They'll probably tell me it's 10 to the minus 9, something, something, something. That doesn't help. So for us to envision what a nanometer is, I want you to look down at your fingernails. Yeah? So in the 5 seconds that you have been looking at your fingernails, they have grown 5 nanometers. Because fingernails grow on average a nanometer every second. But you still can't see it. So how about you pluck a hair from your head? Not you, DP. See, nobody has plucked a hair from their head. How are you going to see it if you don't pluck the hair? Y'all know what it is. So look at the imaginary hair that you have in your hand. That hair is 80,000 nanometers in width. So that gives you an even better idea of how small a nanometer actually is. And of course, if you were to compare the width of the Earth, let's say the width of the Earth is a meter, then a nanometer would be a marble, the width of a marble. So a nanometer is a really small measure. And some would say, why did we want to go all the way down there, and how are we even able to do things all the way down there? So a nanometer is a billionth of a meter, but the good thing about the nanoscale is that you get increased surface to volume ratios. So now you have most of your atoms being exposed to the environment. And because they're exposed to the environment, we can now utilize them as sensors because they're all exposed. Nothing is on the inside. Everything is exposed to the environment. So we get, as we said before, enhanced electrical conductivity, mechanical strength, reactivity, and optical behavior. So for instance, gold nanoparticles. We know what color gold is, right? What color do we see as gold? Yellow. But if we make gold nanoparticles, they appear red or even purple. So the properties have changed, and therefore the particular application now would change. Nanotechnology is also interdisciplinary. So we need the physicists, we need biologists, material scientists, engineers, chemists, all of us sitting down and working on this one thing. So you can imagine the chaos that goes on because everybody thinks that their field is the most important. Yes? But it is very interdisciplinary, and one of the advantages of that is that you learn a lot about the other fields. You also learn a lot about the instruments that exist in the other fields. So key features of nanotechnology. In secondary school, you learned about carbon. Even if you didn't do science, you all learned about carbon, right? You all know about carbon, right? And you learned about the allotropes of carbon. And when I went to secondary school, there were only 2 allotropes of carbon. That is diamond and graphite. Now we have 3 more allotropes of carbon, so we are up to 5. And remember that all these allotropes of carbon only contain carbon atoms. So we have Buckminster fullerene, as you see here, which is a soccer ball that has a soccer ball shape. So because of its shape, we can modify the outside with receptors, and we can put the drug on the inside and have it be delivered to a particular organ. We have carbon nanotubes, which is like a sheet of carbon that is rolled. And you can have single-wall carbon nanotubes or multi-wall carbon nanotubes. And carbon nanotubes are lightweight, but very, very strong, and they conduct electricity. They are better conductors than copper, so really good at conducting. And then you have graphene, and graphene is one of the things that more scientists are excited about. So they used to be excited about carbon nanotubes, and then we found graphene, and they throw away carbon nanotubes essentially. So graphene is the world's first two-dimensional material. It is a single layer of carbon atoms. It is lightweight, it is strong, and it is very conductive. And the reason why they throw away the carbon nanotube is now you have one single layer of carbon, so every carbon is available to us for modification. So now we can, for instance, use graphene as a wound dressing. So you get a cut, we can have a graphene dressing, where on one side we have the drug that would be administered to the cut, and then on the other side, the graphene acts as a barrier to keep out bacteria, water, etc. And all you have to do is apply it directly to the cut, and you will be good to go. So graphene is, lots of stuff is going on with graphene, especially in terms of electronics and drugs. And then we have the carbon dots, which are particles of carbon that are they're less than 10 nanometers, so really small. But these carbon dots, when I tell you they photoluminesce, they give off a light that has a lot of us excited, because now we see applications in imaging, because it gives off a bright, stable light that we can utilize. So we call these C dots, but they're just like quantum dots. We then have, of course, metal-based nanomaterials, where we have nanoparticles that we can make from gold that can be utilized in green chemistry. So we can get rid of catalysts, for instance, that are harmful to the environment. We have things like silver nanoparticles that we can use as antimicrobial agents. So you can think of, for instance, you can take silver nanoparticles and you can purify water with it. Because of the antimicrobial properties, you can also make dressings for cuts, etc., with the silver nanoparticles. We have polymeric nanomaterials that scientists want to use for tissue engineering. So you take this material that is at the nanoscale level and you use it as a scaffold to grow new tissue going forward. Remember I mentioned dendrimers? That's a dendrimer, as you see here. So a tree-like structure where you can have, as I said, the imaging agent on the inside, and then you modify the outside to get it to its target organ. And we have quantum dots, and remember I just spoke about the C dots. So utilizing quantum dots in imaging. That is something that is attracting a lot of attention right now because of the light that is given off and the colors. We can use them in TV displays, for instance. We can use them in imaging, and this table, because it absorbs light very efficiently, we can use it in solar panels. So what are some of the other applications of nanotechnology? We spoke about drug delivery already, quantum dots and nanoparticles for imaging, and tissue engineering, where we can mimic biological structures. So you can see where, for instance, you break your bone, and we can use a nanomaterial to help the bone to mend, to grow back the way that it is supposed to. For those of us who have degenerative diseases and your cartilage is going away, we can use nanomaterials to fill in the spaces where the cartilage has been lost. And of course, if you get burnt, we can use nanomaterials for your skin to help your skin recover. And here we have an example of a wound dressing, and this is actually a biosensor that's applied to a cut. And what this does is that this monitors the environment of the cut. And based on the feedback that it gets from your body, it will then release medication. So it's like a smart material. So it's not giving you all the medication at the same place. It's actually measuring your body chemistry, what is occurring, and then it will release the drug as needed. Because your body, what is occurring in the wound is actually now affecting the supramolecular complexes that are part of this biosensor and allowing it to open and release the drug. And I was hopeful that the new Minister of Innovation, Science, and Technology would have been here today because we had discussions about this. And I don't know if you can see it very well, but this here is a graphene biosensor that she has on her finger that actually constantly monitors her body chemistry. And then you can feed it back into our devices. And this is very unobtrusive. You can hardly see it. It can sit under your jewelry, but it's constantly monitoring what is going on in your body. Here we have electronics, where you can use graphene, as I said before. You can use graphene because it's very flexible. You can have foldable phones. You all know how long we're waiting for foldable phones, right? So foldable phones that you can just put over your wrist, or you can wrap it up like a paper. We can use graphene for that. I am not sure why these phone companies, looking at you, Apple, cannot incorporate graphene into the glass, the screen of the iPhone, or even the back of the iPhone, such that when it drops, it will not crack. Please, let's do that. We also have solar cells, as was mentioned before, and batteries. Now, we have some silicon nanowires that have actually replaced the traditional graphite electrodes in batteries. And what does that do? That means that we can charge the battery faster, and the battery can hold the charge for a longer period of time. So imagine us going to get our electric vehicle. So we buy our electric vehicle, and we only have to charge that battery once a year. Or even better, we buy the electric vehicle from the dealer, and we never have to charge the battery at all. So the different types of nanowires that we can make at the nanoscale level would allow this to happen. We have with the environment, we can do water purification, so we can prepare nanofilters, air purification. We can have, you know those factories when you have the flue stacks and they're releasing the pollutants, right? We can actually make these nets that contain different nanomaterials that would capture these pollutants and then break them down so that they never get out into the air. Food and agriculture is not to be left out. We can use nano coatings to enhance durability and therefore make the packaging more resistant to tears as well as contamination. What does that do? That means that we have an enhanced shelf life for our particular product. We can also utilize nanomaterials that will keep out light, that will keep out moisture, that will keep out air. And not to leave out the farmers, you can see where we can build cages at the nanoscale level, supramolecular cages, of course, and we can then put pesticides or fertilizers within these cages, and these can be applied directly to the plant. And therefore, we use less fertilizers and pesticides, which is cost-effective, but also good for the environment as well. What about clothing? So we can coat our clothing with certain nanomaterials. So for instance, silver nanoparticles, and we know that those are antimicrobial. So you can see them being incorporated into hospital linens, for instance, or medical garments, which means that we do not have to use harsh chemicals to clean them. So we become eco-friendly. And of course, space, because space requires different types of materials. Materials that are strong, lightweight, but also resistant to radiation. So this is just going through some of the advances in nanotechnology. So we have nanorobots. So imagine that you can swallow robots or be injected into you, and it can go in there and clean out blood clots. So your incidence of strokes and heart attacks decrease. 3D nanoprinting. Can I now get an implant or prosthetic customized for me using nanomaterials and 3D printing? Yes. Artificial photosynthesis, we spoke about that, and flexible electronics. And one of the more interesting things is metamaterials. And these materials can bend light around objects. And therefore, if you can bend light around objects, you now have the invisibility cloak, a la Harry Potter, that people can use. So what are the challenges with nanotechnology? First of all, we have no idea how nanoparticles and nanomaterials interact with the environment, interact with us. There are lots of studies that have to be done, and we are way behind in terms of determining the environmental impact. How are we going to take this again and scale it up? I don't think Barbados has any legislation that speaks to any sort of nanoparticles or nanomaterials, any safety standards, how do we dispose of them, nothing like that. So the legislation also has to be developed. And of course, we are at the nanoscale level, and we need these things to be able to maintain their integrity no matter what the environmental condition is. And that becomes a little more difficult when, according to people, you can't see them. So some of the key takeaways for nanotechnology, it is all about working at the nanoscale, developing new materials based on the unique properties that these compounds show when you get down at the nanoscale level. But we must do it in a responsible manner. And now we will come to how are these two integrated? Both of these, supramolecular chemistry as well as nanotechnology, involve the manipulation at the nanoscale level. So all of our supramolecular complexes are nanoscale size. They're nano-sized. And of course, nanotechnology is all about the development of devices and materials at the nanoscale level. So both of them complement each other very well. So we are just going to go through some examples, and I will point out what is the role of supramolecular chemistry and what is the role of nanotechnology. So think about supramolecular chemistry as the building blocks. It is the Lego that is going to make these complexes that can then be incorporated into nano devices. So take, for instance, we can take short strands of DNA, and we can bring them together using supramolecular chemistry to form these DNA nanocages. And within the DNA nanocages, then we can hold whatever we like inside there, whatever feels comfortable inside there. So the supramolecular chemist is all about making the nanocage using these strands of DNA and putting the guest molecules in there, and the nanotechnologist is all about what are we going to do with this? We're going to make a device. Are we going to make an implant? What are we going to do with it? Then we have, of course, drug delivery systems, right? So the supramolecular chemist makes the cage, the vessel that delivers the drug. What does it, and the nanotechnology part is, are we going to make this into a device? Is it going to be on a ring? Is it going to be an implant, etc.? And I just wanted to show this. You can't see it very well. Well, I can't see it very well. This was actually a paper that showed a rotaxane. Remember the rotaxane that led to the soutane? So the rotaxane is actually a mechanically interlocked molecule. And this is the rotaxane here that was made in the laboratory. And what happens is that this is the anti-cancer drug, paclitaxel, that is part of the rotaxane. And this rotaxane is responsible for taking this drug to the cancer cell. So the rotaxane would take the drug to the cancer cell because it has other groups on it that would allow it to get to the cancer cell. And once it gets to the cancer cell, you have beta-galactidose, which would then hydrolyze this galactose. Now, I know I lost you all, but that's biology, by the way, not chemistry. So it will hydrolyze the galactose. But what is important is that in the cancer cells, you have a higher concentration of this particular enzyme, which means that it hydrolyzes this, and what happens is that this ring breaks. So you have organic chemistry at this point. You push arrows, electrons move, the ring breaks. What was the purpose of the ring? Right, so the ring was protecting an ester group, which is here. So once the ring comes off, then esterase, which is present in the cell, would break that bond and free the drug. So that is what we mean by a drug delivery system. The rotaxane delivered the drug, and the conditions within the cell broke down the rotaxane, and therefore the drug was released within the cancer cell and not in the other cells that are healthy. What about biosensors? So the supramolecular chemist would come up with the molecule, the host gas molecule that would bind to the particular analyte. The nanotechnology is all about making the device, the actual biosensor device. And this is part of my work because I also have to show you my work with regard to how both of them come together. So here we were making a biosensor for microcystin LR, which is a toxin that is made by cyanobacterium. And here we see this here is an electrode, and this part here is actually the supramolecular complex that is formed. So we have two different polymers here, and then we put on silver nanoparticles onto these polymers, and then we have thiolated DNA strands that we then attach to the silver nanoparticles. And then this recognizes the microcystin LR once we put it in. And we can see the signal because we have an electrode here. So we can see the signal, and you get a linear response. So essentially, as the concentration of microcystin LR increases, the signal that we get also increases. And these are just images, and you can't see them very well, but these are scanning electron microscopy images of what is happening. So this one is more cauliflower, and then you see it becoming more granular, which means that we have been able to put on the nanoparticles. And then you see the transmission electron microscopy here, where here is the normal polymer, and then you start to see all the black dots which represent the silver nanoparticles that have been deposited on the actual polymer. So we've spoken again about nanomaterials. The supramolecular chemist would make the complexes that would then sit on the nanomaterial. So you can think about graphene as a nanomaterial, and the supramolecular chemist would make host gas complexes that would then sit on the actual graphene. Of course, the nanotechnologist is going to go off and make supercapacitors and batteries, etc. And then with respect to the environment, of course, the supramolecular chemist would make the host that would then seek out the guest. So we can have a guest. So for instance, if we want to extract rare minerals, we can design a host molecule that would be selective for that particular host guest metal ion. Of course, we can clean up water. We can clean up air. Molecular machines and robotics. So what do the supramolecular chemists do? We make the molecules that move, that give motion. And then the nanotechnology part is integrating that into some sort of robotics. So the supramolecular complex may be just at the tip of the robotic arm. And here we have the 3 winners of the Nobel Prize in 2016 that were responsible for molecular machines. So we have Jean-Pierre Sauvage here, we have Fraser Stoddart, and we have Ben Feringa. And this was a stamp from Niger, the country Niger. But it's really interesting because they're holding the wrong molecules. That is not what they were known for. So the catenane is supposed to go over here, the rotaxane is supposed to go up there, and he's supposed to be holding a nano car. I don't know what Jean-Pierre Sauvage is holding over here, but anyway, I thought that the actual idea was good. So what are the challenges when you bring both of these areas together? Same thing, design complexity. We now have to design and be able to control these nanoscale devices, these nanoscale structures with precision. Scalability, how are we going to get it to industry scale? How do these things interact with the actual environment? And of course, how do we integrate it with technology? So I am very excited by AI. I know some people are wary with respect to AI. But as a chemist, a wet chemist, most of my time is spent standing up in a lab, mixing stuff, looking at stuff, doing experiments, saying that this particular thing will work, and then it doesn't work, and then go back to the lab and try something else, tweak one thing at a time. Now we can utilize AI to look at the design of our molecules and tell us whether it would work before we actually go into the lab, which means that we are now saving time and we are saving money. Hallelujah. Yes? There'll come a time when AI can also design the molecules, and then we will have to find something else to do. But until then, I am excited about it. So in conclusion, the takeaway from both of them is that supramolecular chemistry and nanotechnology are not two different areas. They're actually very complementary to each other. I think that nanotechnology really benefited from supramolecular chemistry because we were the first ones to go down at that particular level and show that we can build molecules, we can design molecules, we can make molecules move, and then the people in nanotechnology, most of the physicists and the engineers and stuff like that, came in and said, let's take these molecules and put them on surfaces, put them in devices, etc. So we have a lot of innovation, interdisciplinary innovation that is going to take place in the coming years. So what are the visions for the future? Because we have more and more supramolecular chemists that are coming on board, more and more people dealing with nanotechnology. But I just want you to use your imagination here and think about a time when we can harness solar energy as easily as we breathe. How we can have self-healing materials. So for instance, potholes. Can you imagine we have roads and you have a crack that develops in the pothole and then the asphalt, well, it really won't be asphalt, but whatever material is on the road just repairs itself after a while. Can you think about a sunscreen? Now, that you just don't put on your face SPF 50 or whatever, but the sunscreen responds to the amount of UV light. So you have the nanoparticles, and then you have supramolecular complexes. Think of them like little umbrellas on the nanoparticles that are on your skin. So when there is high UV light, these molecules move and the umbrellas open, which gives you more protection, and then when the UV light decreases, they close. So more of your skin is exposed to the sun to make vitamin D. And then we have quantum computing, which I really didn't talk about. I said I would talk about quantum computing. My students would know the answers to this question, so I asked them to keep quiet. What is the best computer that there is? Anybody knows? The brain. Our brain is the best computer there is, and it does not have a set of metal in it. So we are trying to move away from using metals in computers and using organic molecules, which means that we need machines, we need movement. So we need a molecule that can move and give us a 1 state, and a molecule that can move again and give us a 0 state. And therefore, we start with the quantum computing. And we do have supramolecular systems that can do that already. One of the challenges is when you put the thing on a surface, not all of them behave how you want them to behave. So for instance, I may stand up and I have a ring. Think about a hula hoop I have on me. So up here, if the hula hoop is up here, it's the 1 position. If the hula hoop is down there, it's the 0 position. And then I clone myself millions of times. But when you put me on a surface, some of me is standing up, some of me lying down on the ground, some of me kneeling down. And therefore, we have to look into how we get all of them to behave when we put them together on actual surfaces. And anybody heard about, very recently, the Majorana 1 chip for quantum computing? It came out this week, I think, from Microsoft. Supramolecular chemistry, essentially. So indium arsenide with aluminum, a coating of aluminum. And what is very important here is that it's at the nanoscale level, moving atom by atom and putting them where they want it to be. We now have, according to Microsoft, quantum computing. We're on the cusp of quantum computing with that. It took them all of how many years? 17 years to get it done. So before we go, I just have to pay tribute to my supervisor at the California Nanosystems Institute. He was my postdoctoral supervisor for 2 years, and he passed in January of this year. So he was one of the Nobel Prize winners in 2016. I would like to think that I contributed to the Nobel Prize, but no, what got the Nobel Prize was actually before my time. But he was actually supposed to visit the campus this year. We were planning a visit for him to come down, but he passed away suddenly in January. So I just want to say thank you to him because he did give me the opportunity to switch, because my PhD is actually in inorganic chemistry and electrochemistry, to switch to supramolecular chemistry. And this is when I was at UCLA. I'm sure you can pick me out there quite easily. That was a long time ago, but I believe that I am still the only person from the Caribbean that was ever supervised by him, and probably the only black woman, female as well, that was ever supervised by him. So he has been really good to me. So thanks, of course, to my PhD supervisor, who is Professor Lincoln Hall, who retired. He was the one who essentially pushed me to do my PhD, because at that age, I didn't know what I wanted to do. So he would say, do you want to do a PhD? Sure, I would do my PhD, and therefore I did my PhD with him. Of course, Professor Emmanuel Iwoha, who is in South Africa, who is one of my collaborators, very good collaborators, and that is where we do a lot of the sensor work, the actual building and testing of sensors. To the University of the West Indies, of course, because without them, I wouldn't have any BSc, I would not have any PhD, I would not be standing here. So they have essentially given me a lot. I don't think I can ever give back enough to this particular institution. And I want to say thank you to the National Science Foundation of the United States of America. Given the political climate that we are in, that might no longer exist going forward, but they were responsible for funding my postdoctoral studies while I was at UCLA. So without the funding, I would not have been able to capitalize on that particular opportunity. So thanks to them as well, and thanks to you, the audience, for listening in. And I hope that everyone here at least now knows what is supramolecular chemistry and what is nanotechnology. It doesn't really matter if you don't know how they interconnect, but at least you know what the two particular areas are, and now you can have a conversation with me and other persons about this particular area. Thank you.
So the organic chemist in me is beaming. The female scientist in me is screaming, because I think that we were in for a treat. There was a lot that was said, and I think that she found a unique way of bringing that down to the reasonable man in Black Rock. Maybe? Maybe. So now we get to ask some questions, and the floor is open. I think we have, not quite seeing well. Yes, the light is very special. But if there is any questions that needs to be raised, or do I delve right into my own? But the floor is open. What questions do we have for Professor Williams? Yes, please.
The non-chemist, yes.
Thank you so much. So I have two questions. The first question is, what time and days are your lectures? Because you are an excellent lecturer. Yeah. That was fantastic. So congratulations. I mean, usually I sort of nod off during these lectures a little bit, but I was on the edge of my seat. So really great lecture. Congratulations. I was also interested in what you would have said in relation to the link to a lot of the green areas of your research. So like recycling, and also with battery storage and those type of things. We do have a lot of companies in Barbados dealing with those things. So we have solar PV companies, we have companies that deal with solar water heaters. And at the moment, we don't quite do a lot of research and development in those areas. They're mainly like an assembly country. Do you think it's time for us to maybe move up a level a little bit and start doing a little bit more research and development in those areas? Do you see a benefit for those companies?
Right off the bat, I want to say yes. But of course, everything comes at a cost. And the research that goes into these types of technologies requires a lot of money. And I'm not sure whether our locally based companies are in such a position that they can dedicate that amount of money towards research. But I think that they don't have to do the entire thing. They can do little parts, because our environment is unique. So we can look at what has been done overseas for temperate environments, etc., and see how we can customize it for our environment. And that would require a little bit of research and development, and would be a lot more cost effective than you going out and say, I'm going to find some new nanomaterial that we are now going to put into our solar panels. So I think we can piggyback on what is done worldwide and do a little bit of research for our purposes based on our unique climate and requirements, and allow it to be cost effective. Because I think money is really the problem. Money, and the fact that we as consumers, we don't ask for anything else. We sort of support the whole assembly industry, right? We just consume and don't innovate. I think we have a lot of innovation that can be done here, but it's all about cost, and I understand the cost implications. But you also have to put, and we have people from Export Barbados here, you have to put legislation in place, because you can't have anybody in their backyard just playing around with these nanomaterials and nanoparticles, etc., because then it's going to get into our water supply, it's going to get into the dirt at the side of the road that you breathe in, etc. So we have a ways to go, but I think we need to start small. The other non-chemist.
I am a super non-chemist. But fascinating lecture, Prof. Williams, really fascinating. I'm sure my question might be on other people's mind, and it concerns cancer, Alzheimer's, dementia. where do you see this interconnection between supramolecular chemistry and nanotechnology taking us?
You're asking a biological question there, because that requires me to understand, whereas the cancer is very well researched to understand what causes Alzheimer's and dementia and stuff like that. But if it is, I don't want to delve into that because the biologists that are around are going to correct me and say that is not it. Is it a gene or whatever compound, whatever molecule it is that we are lacking, or maybe we have too much of that is causing these things, then we can utilize supramolecular systems that can deliver the particular molecule that's missing, and this is just hypothetical, if this is actually how it occurs. Or we can have supramolecular systems that move the molecules away, the waste molecules that are produced, we can have them be moved away. So therefore, are ways of cleaning up your environment. So in one way, it's like delivering drugs, in the other way, it's like remediating the environment within your body or your brain or wherever this particular thing happens. Yes, we can utilize supramolecular chemistry for that. We just have to design the host molecule once we know what the target is. And that's for the biologist to determine what the target is. And the supramolecular chemist can design the host for it.
So I'm going to piggyback on that a little bit and talk about it from the other perspective. Any evidence so far that some of these nanoparticles, supramolecular compounds that are being utilized or could be utilized in the body could cause cancers, Alzheimer's? Because we're talking about sunscreens being absorbed into the skin. So where are they in terms of, and I know you said a little bit about it, but can you elaborate to see where they are?
So as I mentioned in my lecture, we don't have a lot of literature out there that speaks to how these nanoparticles and nanomaterials interact with the human body or even interact with the environment. So what do we need? Clinical trials. Not so. We need experiments where people who wear the sunscreen that are made up of nanoparticles, that we can follow them. Do they develop cancer? Do they develop Alzheimer's faster than other people? So we need that sort of experimentation. And unfortunately, the area is moving a lot faster than the studies on human beings and other biological systems. So I guess that is human nature. We go forward and then we find out 20 years later that this particular thing caused cancer back then. So I think we have a lot more to do. I think that the good thing here is that the scientists are aware that these studies have to be done. They are aware that as much as we can see the good in these things, there is also the bad side that we have to consider, we have to hypothesize and do the experiments.
Okay. I think there's another question coming.
Yes, okay. First of all, congratulations for your considerable achievements.
Thank you.
My question was going to be along the lines of the first question in terms of how is the university linking this work with and these capabilities with practical problems. And yes, I understand the issue of the development cost, and it would be more about tweaking solutions to our situation. But I'd like to think that it is happening. My second comment was actually along the lines of what you were mentioning, because for some things, you know, that are so important, like the medical applications, you can appreciate risk when the reward is so great. For something like sunscreens, I mean, when I was following this a little bit more closely, I would have been very concerned about the absorption of nanomaterials, and nobody knows where it's going in the body. So I was surprised that it is being widely used in sunscreen, and I would tend to think I would like to think that there is at least a fraction of the investment in development as in governance of these developments. Otherwise, it can push us back.
So yes, I think with respect to the whole, we are now seeing nanoparticles, and we have been using them for years. We're seeing nanoparticles in consumer products. We're seeing nanoparticles in all the cosmetics. So you know this new generation does a lot of makeup, all right? Use a lot of cosmetics, and there are red flags that are being raised about all the harmful chemicals that exist in these cosmetics and stuff. And along those lines would be nanoparticles as well. So we are aware of it, but it's like I tell my students, you have to weigh your risk, right? Why are you utilizing these things? Is the reward worth the risk? And I always say cheekily, no matter, go ahead and utilize these things, because I have faith that in 20 years, when they say these things cause cancer, that we would have the drugs to deal with the cancer, or the technology to deal with the cancer. So that's my optimism in science, that we are going to move. And so, yes, you can sit and you can worry about these things now, but it's just going to go, it's going to progress. It's like AI. We can sit and talk about AI whole day, but it's going ahead with or without us. So we need to have faith that the scientists are going to come up with remedies for whatever ailments these new materials actually bring to the fore. With respect to the university, there's a ticklish one. Once again, if you're doing things at the nanoscale levels, there are certain safety standards that you have to put in place, but there are also certain infrastructural requirements that you need to be able to do such work. You need to have buildings that are fit for purpose. You need to have a stable electricity supply. You need to have clean rooms, etc., to do this type of work. So we at the university, I would welcome the chance to work with industries in terms of research. But what I do find, and I shouldn't say this, but industries think that science happens overnight. You heard me say that the quantum computing chip took Microsoft, which has unlimited money, 17 years to actually come up with it. So science takes a while, because it's trial and error. Trial and error. You'll be very lucky if you got it the first time out. And so it takes a while, and we as a society in Barbados and the region even need to appreciate that science requires money and it requires time. Now with my collaborators in South Africa, there is a National Science Foundation there as well, where they fund these types of research, and so you have more synergies between the actual companies that exist there and the universities, to the extent that you have companies that actually sponsor laboratories on the university campus and employ students, master's students, PhD students, postdoctoral students to actually come in and do the research. So they fund the actual lab, they pay the students, and they know that it takes time to be done. And there is a vision, right, in that country that they're going to deal with low-income communities and sort of give them the tools that are necessary to help them to better their lives. So we know that South Africa is a much bigger country than Barbados. So you can imagine if you have a farmer out in the rural parts who needs to test something, test the water to see if it's okay for the animals, etc., that farmer is going to find it very, very difficult to send a sample to a laboratory, pay a laboratory, wait for the results to come back, then to say it's okay for the animals to graze here. So development of sensors that the farmer can just add some water to, get the feedback on his or her phone, and be able to say that this water is good. So sort of also supporting and feeding into the UN SDGs, the Sustainable Development Goals as well. But it all comes down to having the infrastructure, having the money, having the talent to get it done. But of course, at the University of the West Indies, we are always open to that sort of collaboration.
Following up on that, and they were all excellent questions that were being raised, but Do you think that the recent thrust towards a bioscience industry creates an opportunity for some of this work to be done now? We know that it will cost a lot, but do you think we're trending in the right direction?
We are. Thank you. So we are now getting to recognize that science is the way forward. In order to progress, we need to tap into science. And I, as a chemist, would say, well, you know, maybe not biosciences. Sorry, Dario, but I am happy that it is biosciences. At least it is something that will now allow for the education of our population and for our population to become more familiar with science, for our population to buy into the scientific method, into the utility of science, and therefore we hope get more students interested in science because they're moving away from science because they consider it to be difficult. So get more students interested in science, build up our capacity, and essentially start climbing the ladder towards first world status. And it has to be done on the backs of science, and bioscience is a really good start because we know that the chemists can dip into the bioscience. We know the physicists can dip into that. The engineers can dip into that. So it's sort of all-inclusive, really. And so I welcome initiatives such as that, and that really needs to be commended. That's a commendable initiative.
All right, I think we have one other question.
Good night. I have a question. How would you validate what you made? As in, if you had to make nano cars, how you know if you made a nano Porsche or a nano Toyota? Because I'd imagine if, as the complexity increases, you can't really use the scanning microscope anymore. If it's, say, thousands of things self-assembled together, you can't really scan it anymore. So how would you validate what you made?
So you can to a certain extent, though, because remember those different microscopes that I showed the images of, the technologies, those technologies are advancing every day. So people are working on being able to see more at the nanoscale level. We spoke about the quantum dots that can actually be used in microscopy because of the light that they give off. But we also have another type of microscope called an atomic force microscope that can be used. And what this does is that at the tip, it has electrons at the tip, and it moves over the surface where you would have your nano car, your Porsche, or your what? Toyota Corolla. Right. And essentially, it would draw for you the different heights of the molecules that are on the surface. So when you take all those traces and you put it together, then you'll be able, by the shape of the car, the height of the car, the width of the car, to determine whether or not you have a Porsche or you have the Toyota Corolla. So we do have these technologies, and I must say that the developments of these microscopes were really propelled supramolecular chemistry forward. Because the atomic force microscope, we can actually move atom by atom and put it where we want it to be. And yes, you can see it because you did, I can't remember the name of the course, second year in organic chemistry, and we showed the nickel atoms lined up. Remember, IBM did it first. They actually used nickel atoms and spelled out IBM on a surface. And in order to do that, they had to move atom by atom and then image it. So yes, we can see all the way down there. It may not look like a car in the way that you think a car would look, but when you put all the data together, then yes, you come up with the car.
All right, I thought that was an excellent question from a current student. I think we have one final question.
Good evening. Congratulations, Professor Williams, very well deserved. I just had a quick question from the perspective of a third non-scientist and also someone sitting in an interesting position related to the sciences. I wanted to know if you touched on it a bit, but I just wanted to get a little more information about what you feel the enabling factors would be to create that ecosystem that allows the region and Barbados to actively participate, even from a preliminary launchpad position, in the world of supramolecular chemistry and nanotechnology.
See, thank you. It rolled off your tongue now because you heard it so many times today. All scientists, any scientist would tell you that you need funding. There is no science without money. You just cannot do science without money. Yes, you cannot do science. Whether you're a theoretical chemist or a wet chemist, theoretical chemists require computing power. The wet chemists require infrastructure. They require consumables. So we need the supporting infrastructure. We need legislation that is favorable to scientists. So when something, for instance, is shipped from overseas, we don't have customs sitting on it for days, etc. So we need to be able to put that sort of legislation in place where they essentially trust the university. So these things are coming to the university and they are confident in what we are going to utilize it for. And of course, we need the talent. So we need to train the students in these particular areas. And we are not saying that all of them have to be chemists. We want physicists, we want computer scientists, we want engineers, we want biochemists, we want biologists, we want everyone because this particular area is interdisciplinary and everyone has a part to play in addressing the different challenges that exist in society, that exist in the environment, that industries struggle with on a daily basis. Everyone needs to come together. So we really have to put things in place to attract students into science and give them a good experience while they're in science so that they can then go back and say, you should go and do science because I feel that this is the way that we are going to cure Alzheimer's, and I would have been a part of that.
All right, they're pushing for one last question, and it's a dean, so I'm going to adhere to let Dean Kohal speak, and then we are going to have to wrap up.
I feel nepotism.
Pleasant good night, everyone, and congratulations, Professor Williams, on a fantastic lecture. So I'm a scientist, but I'm going to ask a non-scientific question. If you were to identify one problem in Barbados, and let's just say the Caribbean, that supramolecular chemistry and nanotechnology can solve, what would that problem be? And what would be your approach to addressing that issue?
One problem, huh? One. That we can tackle. I want to say, for me personally, it could be water, like purifying water, because I think I always had the thought in my mind that water would cause the next war, but that was before the elections last year, right? It might be the second thing that causes a war, water. But I want to say in terms of Barbados, definitely energy. If we can develop systems that would allow us to capitalize and move forward on the solar panels and harnessing that solar energy so that we have electricity and we have our electric cars, etc. I think that more people would be appreciative of that because they would feel it in their pocket. And I don't think that it's such a big leap because you have a lot of scientists who are working on different areas of this. So part of my research is in solar cell technology, and we were looking at, I think every person may have heard about perovskites, but we are looking at kesterites now as being harnessing solar energy. So I think that may be at a point in terms of the technology that we can get in on that, bearing in mind that we used to be a leader in this particular area, and we just stopped for some reason. We put the solar panels on our houses, and we are okay with that, and we just stopped being a leader at that point in time. So I think that before the knowledge of yesteryear is lost, that the younger scientists can still learn from the older scientists and move this forward. I think that the energy aspect of it. But I like water.
So I think that we have had a wonderful afternoon listening and learning some new areas. And so I would like you to join me in thanking Professor Williams for her stirring talk. It was an excellent presentation. I now have the pleasure of calling on Dr. Sherma Roberts, Interim Director, School for Graduate Studies and Research at the UWI Cave Hill, to deliver closing remarks. Thank you.
Thank you so much, Madam Chair. I sat there and I was reflecting on what are the indicators of a good scholar. And I was thinking that you could provoke thought among your peers, but when you make what is not known to those of us who are not in your disciplinary group, then you really are a good scholar. So I really congratulate you, Professor Williams, on making the unknown known to me. So I'm immensely proud of you as a colleague. I'm immensely proud of you as a Trinbagonian woman. And I'm immensely proud of you as a female scientist. So congratulations again. Veteran Trinidadian politician Joan Yule Williams famously said, "If the people don't come, it don't make sense." So an enormous thank you to those of you present in the audience and to all of you who are listening online. On behalf of the School for Graduate Studies and Research, we thank you for participating in tonight's lecture. Your presence here and online and your insightful questions have contributed to making this evening a very memorable one. So thank you very much for being a wonderful audience. Let me also express my gratitude to the Deputy Principal, Professor Winston Moore, for your unwavering support for the professorial lecture series and for your welcome note in which you reminded us of the invaluable contribution that professors make to the academy as well as to the wider society. Professor Emeritus Kawa, thank you so much for your gracious opening remarks. He really aptly described you, Professor Williams, as a brilliant daughter of the Caribbean, and he really highlighted your persistence in developing and designing suitants that can really help us improve our lives. To Dr. Luke, we thank you for your reflections on Dr. Williams as a role model, as a groundbreaking researcher, and as an inspiring lecturer. Nothing happens on the campus without exceptional teamwork, and so I wish to thank the director of UETV and her team, the EBCCI, Lanix Catering in place, and all the offices that contributed to making this event a success. I cannot end without thanking the Madam Chair for your gracious chairing of this evening's event. I also want to single out the School for Graduate Studies and Research for hosting this professorial lecture, and in particular, Ms. Suzanne Chandler for always giving human service behind the scenes each and every time. So ladies and gentlemen, we bring this evening to a close and we say thank you very much for being with us. Do join us for cocktails, and when you hear supramolecular chemistry and nanotechnology, you will not be stumped. Do enjoy your cocktails. Good evening.